Good morning, further 3-4 students. Welcome to the normal distribution class. Normal distribution is one of the coolest features of statistics all around. It is used everywhere. That's why it's called normal, because it just happens so often. Alright. So, by way of introduction, it was created by, or discovered, I guess, by a man named Gauss, is sometimes called the bell curve, although this is a little controversial. Alright. It appears everywhere in probability and everywhere in nature. So much so that, well, we call it a normal occurrence. For example, if you toss 7 coins 25 times, I did this in an experiment, it was great fun, then this is the frequency outcome distribution. So twice there were 7 heads, once there was 0 heads. 5 times there were 4 heads, 5 times there were 3 heads. And this is it on a curve, or on a histogram. And you know we've created a curve by simply joining the top of each portion of the histogram. Similarly, we could toss a pair of dice. And as we toss a pair of dice, we add the totals together from 2 to 12. And if I did this 39 times, for example, I would get that outcome once, 12 once, and 2 once. But in the middle, it happens far more likely. And if I plot the frequency of each number happening, so each number happening is on the x, frequency is up this side, and I can create a curve. Now these are relatively small sample sizes, 25 and 39 is quite small. As I build more and more, throw more and more dice, throw more and more coins, this will become more like a curve. And I am famously terrible at drawing these curves. You'll see an actual curve down the bottom. Alright, let's look at more things. Blood pressure, width of flowers, hand span, weight. Essentially, what these curves say is that lots of people are between 70 and 80, and there aren't that many people between 1995 or 50 and 55. We have a central region that is more heavily populated than the outer regions. And you can look around you in the class or in the street, and you'll imagine that, yes, this is where most people are. If you're up this end or down this end, there are fewer of you. And this occurs in surprising places. So this is the distribution of wide receiver 40-yard dash times. So if they measured American football players running, how fast it took them to run 40 yards, this is the 40-yard speed here. And you can see that, well, lots of people took in between that region there. And if you plot a curve, yes, you can imagine it going more steeply, perhaps. That goes through all there. Similarly here, life expectancy. Lots of different things that I grabbed off the internet to with bats, hydras, Bengalese finches, all have this similar curve. Sometimes it is steep and narrow, sometimes it's like that, but either way there is a certain curve to it. Even the stock market, percentage returns, you can see some years people got really lucky and made 30 to 35% returns on average. Other years, namely the Great Depression, didn't go so well, but you can also imagine a curve through here. Alright, so the normal distribution curve is so predictable that we can actually predict the amount of the population within each portion of the curve. And remember how last video we talked about histograms being associated with the mean and standard deviation. That's what the normal curve is built around. So normal curve looks like this, where, and I'm sorry about the notation, it is essentially interchangeable. X bar or mu is the mean, Sx or rho is standard deviation. If I were you, I would use X bar here and S there. It's the way we've been doing it, or we'll do it more in class, but they do jump in and out, depending on which textbook or which diagram you look at, so it's best you see both. In further, we will use X bar and S far more often. So what does that actually mean? This means that if we have a mean, and then we add one standard deviation onto it, there will be 34% of the population in this section. Now that's rather abstract, so let's take a more concrete example. Take the hand measurement scale here. if we're told that the mean is 10 centimeters and the standard deviation is 2 centimeters, we can say, well, mean is 10 down there. And if I add 2 centimeters on to 12, 34% of people will have a handspan between 10 and 12. Similarly, if I take 2 off, x bar take x, s, and draw 1 at 8, this is saying that we predict that 34% of people are between 8 and 10 centimeters of handspan, and therefore plus or minus 1 standard deviation, so plus or minus 1 standard deviation for 68% of the people. And this is often called the 68, 95, 99.7 rule. So when you hear that something is normally distributed with a mean and a standard deviation, you can instantly plot in your head what the shape will look like and how clustered everyone will be around the center. Right? Most famously, this was used with IQ tests. So IQ is normally distributed, as are in fact your ATARs at the end of the year. For example, if you take an IQ with a mean of 100 and a standard deviation of 10, that would mean this point here is 100, 110, 120, 130. Which means if you're scoring 130, you're in the top 0.15% of the population. On the flip side, if you're scoring 70, then you're in the bottom 0.15% of the population. Right. So, how would this look when we change the distribution or change the standard deviation? Here, we have a mean of 0. And then we change our standard deviation. You can see standard deviation here of 0.75 means the curve is much, much taller and thinner. So 0.75 would fall about there and here. And what we're saying is that 68% of the curve falls in between those red lines. And you can imagine, if we're talking about the blue curve, that yeah, that green highlighted section could well be 68% of the blue curve. Let's take the other extreme with a standard deviation of 2. Standard deviation of 2 means that between here and here, that long black curve going up there, it's saying that 68% of the population fall in there. So both of them are normally distributed curves, they just have adjustable standard deviations. But either way, the 68, 95, 99.7 rule holds. Now, what this actually looks like in an example, please copy it down. At a qualifying meeting, the time taken for athletes to run 400 meters follows a normal distribution with a mean time of 52 seconds and a standard deviation of 1.5 seconds. Now, every time I see this in worded form, I take it aside and just draw myself a quick curve. So a curve has x down here, frequency we barely even write. The mean is 52. Now, if standard deviation is 1.5, 53.5 and 50.5. If you're unsure where to draw it on your curve, it should be approximately the place where the curve goes from concave, meaning like that, to convex, meaning like that. You see how the curve will go concave to convex. At this point is where the first standard deviation should be. If you're doing calculus later in the year, then yeah, you'll get to do that more accurately. But right now, for just a sketch, we want to sketch this out. Alright, so that's one standard deviation out. Let's go another out. Here would be 49, and we want this distance to be about the same as that distance. I haven't done very well. And this here would be 55, and then we wanted another one on. 56.5, and take another one off 47.5. Right. What percentage of athletes had times between 49 seconds and 55 seconds? Alright, so we're looking at what percentage had between 49 and 55. Alright, well, we head up to our rule above and say, well, that is 2 standard deviations out and 2 out. We know that in between there is 95% of the distribution. Note that for further, they will always ask you about 1 standard deviation either way, or 2 standard deviations either way, or 3 standard deviations either way. They won't ask what percentage are 2.5 standard deviations above. We just go on the whole numbers of standard deviations out. And you can approximate from there on, but they will always ask on exact numbers of standard deviations up and down. What percentage of athletes had times less than 50.5? So 50.5 is here. What percentage had less? Well, if we head up to our table, and you'll have it on your notes page, you can see that in this section there was 13.5, so let's head down. $13.5. This here had 2.35, and this here had 0.15. All in all, we have to add those percentages together. So 2.5 plus that is going to come to a total of 16%. So we would predict that 16% of athletes had a time less than 50.5 seconds. Now there weren't many right at this end, because that's where the freakishly fast ones are, but the 13.5%, so quite a few of them, fell between 49 and 50.5. If 100 athletes were at the meet, how many on average would be slower than 53.5 seconds? Running out of colours, 53.5 seconds. 53.5 is here. So how many are slower than that? Well, we have 34 here, 34 here, and then we know that all of those three will add to 16. So 34 and 34 is 68, 16 and 68 is, I'm quite lazy, 84. So we would say that 84% lower, and because it's 100 athletes, which is nice for us, 84 athletes. All right. So important working for this is when you're asked about a normal distribution, sketch the distribution, clearly label 1 standard deviation out, 2 out, 3 out, then look at your notes and answer the percentage questions from there. Alright, thank you very much. Next question, next video rather, Z scores.